All right, in this lesson, we're going to continue to talk about solving quadratic inequalities. Okay, last time we talked about 4 methods, right? Actually, we have a 5th method. The 5th method is something I'd like to start with, and we look at our homework questions, right? I'm going to make the first example from our homework. Okay, the first example is solving for x, of course. Right? And what we wanted is we want to have x squared larger than or equals to 2. You can use all the other methods, no problem. But here I'm showing you the 5th method, okay? When a perfect square is present and the rest are just numbers, right? Just as constants. In this case, you don't have to go through those methods. You can just solve it by taking absolute value on both sides. Okay, so here in this case, you can take absolute value on both sides. So this is the 5th method, or you can call it whichever one. Okay, and then the absolute value on the left-hand side will be greater than or equals to 2, square root of 2. Okay, and then if you recall that we talk about solving absolute value inequalities, right? Then in this case, it's greater than or equals to square root of 2, right? So if this is true, then omega would be either less than or equals to negative square root of 2 or greater than equals to positive square root of 2. So we're going to use this model. We're going to use this model. Okay, so we use this model, and of course, our omega is x. Omega is x. So solution found. Solution found. Okay, so if you have a perfect square, and in the similar case, right? In this similar case, then you can solve the inequalities that way. And let me give you another example, right? Another example that you could have used this method, right? For example, suppose we ask you to solve for x, right? Where you have for one way or the other, you have x plus 1 squared, right? Less than equals to 5. Right? In this case, then you don't need to break it up or FOIL it, right? You just take this piece, right? And you take square root on both sides. Take square root on both sides. And then it's absolute value on the left-hand side, which is x plus 1, less than equals to root 5. Right? And then we have the other model for solving absolute value inequality, and we can just use that, right? If if the absolute value of omega is less than or equals to, in this case, is square root of 5, right? Then omega is between negative square root of 5, right? Less than equals to omega, and less than equals to square root of 5. So we can use this model. You can use this model. In that case, the answer is very close to us. And of course, here the omega is x plus 1, right? And then you just have to subtract 1 on every side. So you have a negative root 5, right? So subtract on every side by 1. Okay, so this side you subtract 1. And this side you subtract 1. And that side you subtract 1. Okay, and then x is solved. X is isolated. So x is isolated. So that's the solution. Solution is already found. You can see this fifth method is very convenient if you happen to have a perfect square in your situation. Okay, for that matter, if it's power 3, power 4, power 7, it's all possible. You can all try those methods. Try the similar method. Okay, of course, the details, you need to pay attention to the details. Okay, so this is the fifth method. Okay. The last 4 methods we talk about, solving quadratic inequalities, actually they're all about sign. They're all about signs. Okay, they're all about signs. They're all about signs. And now I'm going to give you some more examples. Let's look at some other cases. And this example is example number 3. Okay, we don't have a factor form. Okay, but we want x squared minus 5x plus 6 is less than 0. So we factor, right? We make it into factor form. And then we set it equal to 0. Why do we set it equal to 0? We talked about this last time. Well, we set it equal to 0 is to identify where the product change signs. Okay, where the product changes, I think it should be S, right? Changes sign. So once we identify the point where it changes sign, then we can go about the same method, right? If you like the visual, or you like the table, or you like the function method, any method you want, you can just use them. And here I use the sign method, right? You plug in any number into x minus 2. If that number is less than 2, x minus 2 is going to be negative. At 2 is going to be 0. Larger than 2, going to be positive. For x minus 3, we do similar things. You pick a number from here, right? You pick a number from here, you plug in here, and if that number is less than 3, it's a negative. Equal to 3, 0. Larger than 3, positive, right? And in the end, we get to see the product. We get to see the product. Okay, so you pick a number. You pick a number. Okay, from here. And this number will plug in x minus 2 and x minus 3. For x minus 2 is negative. For x minus 3 is a negative. Negative times negative is positive. For exactly 2, we have a 0 in the factor, right? Because 2 minus 2 is 0. 0 times anything is 0. So this product becomes 0. If you pick a number here, you plug in x minus 2 and x plus 3, you have positive times negative. Positive times negative is negative. If you pick a number from larger than 3, right, x minus 2 will give us positive, x minus 3 will give us positive. Positive times positive is positive, right? You see, we talk about this method. It's very visual. It's very visual. And in the end, because we want to have solution for the product to be negative, therefore the solution is going to be between 2 and 3, because for these values between 2 and 3, the products are going to be negative. So that's where we find the solution. If we use the function method, you can see how function method is consistent with what we have done here, right? If it's a function method, then you have a function, you factor it, you identify x-intercepts, right? You identify x-intercepts. Once you identify the intercepts, the x-intercepts, right? What you can do is that you can plot the graph, right? Sketch it is fine. And just tell the reader these 2 points, and knowing that we want the product to be negative, so underneath the curve, right? So this piece of curve is negative. This piece of curve is negative, right? It's negative, and these are positive. We don't want positive, we want negative. So the input that produced the negative output will be between 2 and 3. So the solution is between 2 and 3, right? So these 2 methods are very visual, very visual. Okay, try other methods if you want to. So let's look at this, the 4th example. This is example number 4, right? So we have x squared less than or equals to x plus 2. Okay, in this case, we're going to make 0, right? Why make 0? Why make 0? Okay, I'm going to explain you why make 0 after this example. When we don't have 0, we make 0. Now we make 0 and we find the points where sign changes takes place, right? And then we plug in and we determine the sign. So this is a very similar situation, right? So for x plus 2, x minus 2, so the sign distribution is determined, so the solution is found. Solution is found, okay? If you look at the function perspective, right? If you look at the function perspective, you just have to identify x-intercepts, right? And this time the x-intercepts are drawn as dots instead of circles, right? So in these cases, circles, because they're less than 0. Here we want less than or equal to 0, so we draw dots. We draw dots, okay? So now let's answer that question, right? Before that, look at this, right? You can see the 2 methods we just used, they're consistent, right? So this piece is basically a simplified version. It's basically a simplified version of the function of the picture, right? So this picture tells us, right? So let me just scoot over a little bit, right? They basically tell us the same thing. Same thing, the very same thing, right? They're lined up, right? I try to line them up so you can see it, right? You can see it. So this picture tells us the function when the input is less than -1, the function is positive. When the input is between -1 and 2, the output is negative. When the input is larger than 2, the output are positive. And this picture tells us exactly the same thing. The function picture tells us the same thing, okay? And we already did this one, right? But number 4, which is the first question we did, it can also be done in this way, okay? Doing the factoring way. So here, I'm not going to complete this. I was just, you know what? Maybe I should complete it, right? Maybe I should complete it. We did this one on the first example, right? We did this one on the first example. So let me just complete this. Okay, it's not good that I don't complete it, right? So, so I'm going to take this one to join my first example. To join my first example. Right. The reason why you see this is because I have I've done a recording and then I have to redo it. I did over 1 hour recording. I have to redo it because I messed up. I messed up at a pause and not pausing. So anyway. So if I solve this one using another method, right? Using another method, which is using the factoring method, right? So you have these factors. And you can still do it. You can still do it. What you do is that you have number line, right? This number line, you have a place, which is -√2. okay, negative root 2. Okay, and the other place, and of course, at a negative, so you're gonna look at the sign of x plus root 2. Okay, then you have signs that are negative. If you pick a number less than root 2, at 0, at negative root 2, okay, larger than, and on this other side, larger than negative root 2, they're going to be positive. They're going to be positive. Okay, and for sign of x minus root 2, right, sign of x minus root 2, right, you have a number line again, and you will have a root 2 right here, number line. Okay, so when you pick a number less than root 2, it's going to be negative, right? At root 2 is going to be 0, and larger than root 2 is going to be positive. And in the end, you look at the sign of the product. You look at the sign of this product. It's very similar. It just takes longer. It just takes longer, right? So you can see the first method is much easier, isn't it? The first method is much easier. Number line again, right? You have a negative root 2 has a spot here. And root 2, you have a spot here. Right? So then you look at the product, negative times negative when a number is picked less than negative root 2. So this is going to be negative times negative. That's going to be positive. And at negative root 2, that's going to be 0, right? And larger than negative root 2, that's going to be negative. Oops. What's going on here? Negative. Okay, that's going to be negative. And at root 2, it's going to be 0, right? And larger than root 2, it's going to be positive. That's going to be positive times positive. Same thing, okay? And at this point, I think you have made up your mind which method you're going to use in this case. And you're going to have the same result. You're going to have the same result. That's the solution. That's the solutions, right? That's the solutions. So now let's fast forward. And of course, function method is similar, right? We're not going to do every method for everything, but here I'm going to explain to you or review with you about some of the properties on solving inequalities. Okay, so review. We haven't get to use them very much. We use some of them. We use the one that's okay, right? Review properties to solve inequalities. Okay, we have learned principle number 3, number 4 about equations, right? If A is B, then A plus C is B plus C. If A equals to B, then A times C is equals to B times C, provided C cannot be 0. For inequality, however, right? If you have A less than B, then A plus C is less than B plus C. No change in the inequality sign. If you have A larger than B, then A plus C is larger than B plus C. So that's no problem. What happens is that if you have multiplication, if you multiply by C, we will have some nuances here. If we multiply by positive, right? So if A is larger than B, but we times C on both sides, and C is positive, and there's no change. You can see these two, no change. However, if we multiply by negative, If A is larger than B, that would turn into A times C less than B times C. Then you wonder why. You wonder why. Well, this is why. We know that 3 times 2, 3 is larger than 2. So if we multiply 5 on both sides, 15 is still larger than 10, no problem. But if we multiply both sides by -1, -3 is no longer greater than -2. In fact, it's reversed. So from 3 larger than 2, when we multiply by -1, -3 is going to be smaller than -2. That's why we have this principle. That's why we have this principle. Okay, so these two principles are the nuances we must observe. And you can see from the fundamental level, it completely makes sense. Okay. And the other thing we want to explain to you is why making 0. Why making 0? Right? Why make 0? Why make 0? If you look at the method we talk about, right, the 5 method we talk about in the last lesson, in the last lesson, right, method 1, method 2, method 3, method 4, the 5 method, they're all around, it's all about making 0. For example, look at example number 1, method 1, right? Method 1, we compare with 0. Right? We compare with 0, right? Method 1, we compare with 0. Method 2 is also compare with 0, right? One side is greater than 0. Whether you do tables or not tables, it's about comparing with 0. The function method is about comparing with 0. You see that? And the logical method is also about comparing with 0, right? Positive, positive, negative, negative, right? So all of these methods actually is about comparing with 0. It's about comparing with 0. Why comparing with 0? Because it's easier. It's easier. And the other reason, not only because it's easier, is because if you look at the 3 principles out of the 6, the second principle has something to do with 0, right? Anything add 0 stays the same. Principle number 5 and number 6, which talk about sign, right? Or 0, if A times B equals 0, then A is 0, B equals 0. This principle is used a lot. Number 6 is used a lot in solving inequalities. Right? Yesterday we talked about that if A times B is positive, then both are positive or both are negative. If A times B is less than 0, then the two numbers have an opposite sign. Right? You can see they're all about comparing with 0. And comparing with 0 is much simpler and it makes things easier. And besides, comparing with 0 also connect us with x-intercepts in the function context. Okay, so for this reason, right, in our previous examples, that's why we make 0. Okay, and if there's no 0, we make 0, right? So let's look at some other examples. And this example I'm going to show you is this should be number 5, right? Example number 5. Example number 5. And for this one, of course, it's still solve for x. Solve for x. Right? The inequality we have here is x squared. It's larger than 3 times x plus 6. This is one of the homework questions. There's no 0. There's no zero. Are there factors? We do have a factor on the right-hand side, right? We do have a little factor on the right-hand side, but then where do we start? Where do we start? Right? You basically compare this function with that function. Oops. Right? And would it be easier we compare with zero so we can find methods at our disposal? Why not? Why not? Right? So the first step we're going to do is make zero. Make zero, right? Making zero, so we're going to, of course, we're going to FOIL on the right-hand side. So we have x squared minus 3x minus 18 larger than zero. So now we have made a zero. You can factor. If factor is hard, we can do function, right? So let's factor this piece. There you go. Okay. We got the factor, right? So if this is true, then this is true. If this is true, then this is true. So we larger than zero. So which method do you want to use? You want to use function method or use sign method? It doesn't matter, right? So then you're going to set this piece equal to 0 to identify the points, right? To identify the points where the sign change takes place, right? So we have x plus 3 equals 0. So which principle are we using here? We're actually using principle number 5, right? So we have x minus 6 is equal to 0. And then we get x equals to -3 or x equals to 6. There you go. Okay, so we have identified the point where sign changes. If we decide to use a function method, right? If we decide to use a function method, we're going to make that function. And that function is not going to be this one. It's not going to be this one. It's going to be the one that compare with 0. I mentioned this idea. This idea is very, very important. You're going to encounter this idea once again when you're taking Calculus 3 and many times in between now and when you take Calculus 3, okay? All right, so this function, we know the x-intercepts, right? So these are the x-intercepts. We have identified x-intercepts for this function. So what are they? So these x-intercepts are -3, 0, and 6, 0. Right? And we want that function to be positive, right? So when you actually work these questions, you don't have to draw the perfect picture. You can actually draw, you know, this is opens up, right? We know this parabola opens up, right? Parabola opens up or concave down. I'm sorry, concave up, opens up. So you know, right? You can draw a number line. Okay, it doesn't have to be so complicated, right? You don't have to draw 3. There's a -3 and there's a 6. There's a 6. And you can tell the reader, right? It's going to be, because it opens up, so the parabola is going to be like this. So you can totally just sketch it like this. Right? It's not perfect, who cares, right? You convey the idea. You convey the idea. Okay, you convey the idea. Okay, and of course we have better tools. So you either use this one or just graph the function. right? So here I'm going to graph the function because I can, right? Okay. So here is, okay. And so here I need to have some points and circle or dots to mark the x-intercepts, right? So what do you think? Should I use circle or dots? Should I use circle or dots? I should use circle, right? Why circle? Because it's larger than 0, right? So I'm going to make the circle. I'm making the circles. There you go. So you can see this picture or this number line, they're very much consistent, aren't they? They're very much consistent. Whether you draw, it really doesn't matter which one way you draw it, right? For this picture, you can put a circle. Where is it? Circle. Right? You can put a little circle here. You can put a circle there, right? I pretend I'm drawing on paper. You can use either one. You don't have to show both. You can use either one. That's what I'm saying. To express, to convey the ideas. And what do we want the function to be? We want the function to be positive, don't we? We want the function to be positive. Okay. We want the product to be positive. We want the function to be positive. You can see logically we get to this point, right? If this is true, this is true. If this is true, this is true. This is true, this is true, right? So all these work tell us that the solutions are x less than input less than -3 or x is larger than 6. And I would like to mark those on my picture. I'd like to mark those on my picture. Okay, so I'm going to mark those on my picture. Okay, with something that will show clearly. It doesn't have to be colored. Okay, you can darken, right? You can darken or you can boldface what you write, right? So these two pieces clearly marked. You don't have to show both, just either one. If you show on the number line, I would recommend you mark it somewhat like, it doesn't have to be hard, right? Something like that, with a little circle, marking this point, right? Marking these points. That's good enough. That's good enough, right? That's how to show your work. Okay. All right, so let's look at some other examples, right? So all of these examples we have encountered so far is they can factor easily. But what if it's difficult to factor? Okay, I wouldn't say cannot factor. We know that we can always factor, but sometimes factoring is difficult. Okay, excuse me. If factoring is difficult, what can we do? We have 5 methods, right? We have 5 methods. So let's look at the next one, right? We're going to look at example number 5. Okay, I'm taking an example from our homework. 6, sorry, this is number 6. Okay, and this one, we have x squared plus 2x plus 3 greater than or equal to 0. Greater than or equal to 0. Okay, of course, it's still solving for x. Solve for x. Okay. factoring is going to be difficult. You can try it. You can try it. But I assure you, this one is very, very difficult to factor. Okay, so you can pause this lesson right now to try to factor yourself. And then you come back to tell me, you know what, it is difficult. It can be factored, but it's difficult. Okay. And since it's difficult to factor, so it's difficult to identify the x-intercept. Okay, let me say it again. Since this is difficult to identify, since it is difficult to identify the factors, therefore it's very difficult to find x-intercepts. And we know that as a parabola, as a function, we may have 2 x-intercepts, we may have 1 x-intercept, we may have 0 x-intercepts. So what can help us to quickly identify the factor, whether or how many x-intercepts we have? The discriminant, that's right, b squared minus 4ac. Okay. What is b? What is a? What is b? Right? A equals to 1, b equals to 2, c equals to 3. Look, we have 3 nice, neat numbers here, right? And b is, this is 2 squared minus 4ac, 4 times 1 times 3. And we got a 4 minus 12. 4 minus 12 is negative. What does this tell us? What does it tell us? What does it tell us? It tells us the curve has no x-intercept because this parabola opens up, right? So no x-intercepts. No x-intercepts. And parabola opens up. Okay, you picture that in your mind. What a picture you see. What a picture you see. If you draw a rectangular system, you just sketch it. You just sketch it. It doesn't have to be perfect. What do you see? In your mind, that parabola is going to be what is how it's going to look like. It's going to look like this. It doesn't matter. It could be here. It could be there, right? It could be anywhere, but it's not going to touch the x-axis, right? So even if you don't have a calculator, is it a big deal? You already have the knowledge. You already have the knowledge to identify the situation. Okay. So this is the picture you could picture. The parabola completely above x-axis. If you really want to see where it is, how it looks like, which really doesn't matter. Okay, so let's have a picture here anyway. Okay, so let's have a picture here anyway. Okay, so I'm going to put that picture, if that helps. Okay, it's actually entirely unnecessary. That's the picture. That's the picture. Don't forget our target. Our target is to have this function larger than 0 or equal to 0. Now, from this word, we know that equal to 0 is not going to happen, not in a million years. So larger than 0. So everywhere, every input whose output is larger than 0, isn't it? So what will be the solution? What will be the solution? The solution is all real numbers. The solution is all real numbers. So this time we get to use a discriminant. So discriminant can give us a whole lot of information. The discriminant can give us a whole lot of information. Okay. All right. All right. Can this be counted as a sixth method? I don't know. If you talk about methods, yes, this method can be used too, right? All right. But we understand it's all about signs, right? It's all about signs. So let's look at example number 7. Example number 7 is 2x squared plus 4x plus 1. I'm going to create this method. Okay, I'm going to make it less than equal to 0. So I take a question from the homework and I tweak a little bit. Okay, on the homework is larger than equal to 0, but here I make it less than equal to 0. Okay, so I tweaked it. Okay, solve for x. And of course, you may think about factoring. Let's try factoring. Why not? Why not? Right? Let's try factoring. Pause the recording and try factoring. Right? What have you found? What have you found? I'm going to pour a little, pour some tea for myself. What have you found? Pause the recording. It looks like it's going to be difficult to factor, right? It's going to be difficult to factor. What do we do? What do we do? Right? We need to find x-intercepts if you use the function method. And if we don't use function method, we use the sign method, we need to know where it changes sign, right? So we need to know where the function changes sign, no matter which method we use. And we don't have a perfect square here. Of course, we can make a perfect square if we want to, right? Do you think you want to try making perfect square? How about we try that? Okay, how about we try that? Okay, so I'm going to give you method 1. I know you might be thinking b squared minus 4ac, okay? If you think that way, I'm so glad to hear. Okay, but here I just want to take a little detour. And I'm going to use that as well, okay, just later. So we're going to do the we're going to make a perfect square to see what you get. And from perfect square, what do we get? Why do I think of perfect square? Because I think of, I can factor, I'm taking these two, right? I'm going to factor out the 2, right? Then I'll have x squared plus 2x and the plus 1 still outside. I'm just going to leave it there because I see it might be just a little bit easier to factor, right? So I'm going to plus 1 minus 1. Right, so I'm adding 0. And so in this piece, I actually get a perfect square pretty easily because these 3, hold on, right? These 3 makes a perfect square, right? Everybody knows that. And all of these together, so I'm gonna just write it down this way. So these bracket, inside this bracket, I have a perfect square. Of course, the plus 1 is outside. We must have it tag along, right? So this piece is x plus 1, x plus 1 squared. X plus 1 squared. Okay? And then what I do, I'm going to distribute the 2 to x plus 1 squared, okay, without foiling it. And I'm going to take the 2 multiply -1, so I get a -2. And I have a plus 1 waiting for us, right? And so in the end, what are we getting? We get a perfect square part, and we have a subtract 1. We actually find the vertex. Where's the vertex? The vertex the vertex is -1, -1, right? Because x minus -1 is +1, x plus 1. So this is the vertex. And this parabola opens up. This parabola opens up. So we know that we are going to have x-intercepts. We're going to have x-intercepts, right? Do we really need a vertex? No, we don't. We don't, okay? I'm going to take this piece, right? So from this piece, I'm going to set this piece less than equal to 0. Less than equal to 0. Because this piece is the same as this piece, right? We have a series of operations. And now what do we do? Now what do we do? We're going to add a 1 on both sides. We're going to add a 1 on both sides. Okay, so this is going to be less than or equals to 1. And then what? We're going to divide both sides by 2. So we have x plus 1 squared less than equals to half. And then what do? We take square root on both sides. We're going to take square root on both sides. Taking square root on both sides. On the left-hand side, we get x plus 1 inside the absolute value less than equals to square root of half. That's √2 over 2. Okay, which we are pretty familiar with that piece. And then what? That's the absolute value inequality. That's absolute value inequality. Okay, this is absolute value inequality. And what is the model? We talked about these kind of models before. So the absolute value of omega, in this case, is less than equals to √2 over 2, right? So if then omega is between -√2 over 2 and +√2 over 2. There, right? So we're going to take this model and plunk it right here, right? And what is our omega? Our omega is x plus 1. So we put it right here. Okay, and subtract 1 on both sides, on all 3 sides. I'm sorry, subtract 1 on all 3 sides. And so what do we get? We get -1 here. I'll get a -1 here. We're finished. We're done. We're done. Okay, we are done. That's the solution. That's the solution. It's not nice and neat. And do we encounter these sometimes? Yes, of course. And this is the first method, right? So I kind of take a detour, kind of make you guys think, right? Sometime when completing a square may be an option on the table. So now let's look at a method 2. I know you probably would have done that earlier. Okay. Method 2. Method 2. It's difficult to factor, and we don't know where it changes sign, right? So what do we do? And we may be thinking, when does it cross the x-axis, right? So we're gonna just work out the b squared minus 4ac. And what is our ABC? A is 2, B is 4, C is 1, right? Once we get this, So we got 4 squared. Oops, 4 squared minus 4 times 2 times 1. What do we get? We got a 16 minus 8. 16 minus 8 is 8. Okay, anticipating that if we want to find the x-intercept, we're going to have to use a quadratic formula, right? So we're going to find x-intercept. So we're going to set, right? We're going to set this piece equal to 0. Why do we set this piece equal to 0? To find x-intercepts, right? In that, and we vision that we're going to use a quadratic formula, right? In quadratic formula, there's a square root of d, right? The square root of d. So maybe we just get that done, right? Square root of d is the square root of 8. And we simplify that. Square root of 8 is 4 times 2 taken square root. Right? So we get 2 times square root of 2. So we set it equal to 0. Factoring is hard. Of course, we're going to use quadratic formula. Quadratic formula give us what? 2a minus b plus minus, okay, you don't see that's minus sign, 175%. I'm making the fonts larger. Plus minus square root of d. Right? Quadratic formula. Quadratic formula. And what does that equal to? We just plug in the numbers. A is 2. B is 4. Right? And the root D is 2 times root 2. We already found it. Okay. And then we're going to simplify. Yes, we're going to simplify. How do we simplify that? The denominator is a 4, right? And then this 2, and this 2, and there's a 2 inside. So let's just do it, you know. So negative 4. So I'm going to take the negative 4 divided by the 2 times 2, which is a 4, plus minus, I'm taking 2 times root 2 divided by the 4, or 2 times 2, right? 2 times 2. Simplify it. And what do we get? Here we get negative 1. Plus minus, one of the 2 is reduced. There. What does this tell us? This tells us that for this function, right? For this function, right? So you may introduce a function here. Which equals to this piece. Right? This function has 2 x-intercepts. X-intercept, let me turn on the light. Okay, 2 x-intercepts. What are these 2 x-intercepts? One is negative 1 minus root 2 over 2, comma 0, right? This is a minus. And the other x-intercept is minus 1 plus root 2 over 2, comma 0. That's where sign changes takes place, right? You can see all of these effort we make because it's a hard to factor and we have to use a quadratic formula or completing a square to find where the sign changes takes place. You see that? Okay, do you see that? Same idea. So do we need to know the vertex? In this, we don't really need to know the vertex. For example, we did not need to know the vertex. Sorry, we do not need to know the vertex. Okay, we really just need to know the x-intercepts. Okay, and these 2 points are not nice and neat. Okay, so if you draw that picture, right? So if you draw that picture, you still need to identify these points precisely, right? Your professors would like you to identify those points precisely. Yes, they do. Those math professors, they're obsessed with precise value. Okay, so you have this picture. Okay, so let me organize this picture just a little bit. Wait, what am I doing? Okay, I need to change the view. The view is going to be like this. Maybe 1, -5. Okay, let's just try this. There you go. You can see it's very difficult to identify those points. So we have to use the analytical method to find those points. Now we find them, right? Now we have found them. And we want the function to be less than or equal to 0, right? We want the function to be less than or equal to 0. So now we can just put the points on the graph. I'm going to put that red. Do you think it should be dot or circle? Dot. Why dot? Because less than or equal to 0. So now you look at this picture, right? Now you look at this picture, which is which? Which is which? Which is which? This is the 1 point, and this is the other point. You can see it's very difficult to identify the points from the graph. So that's a limitation, right? But with the quadratic formula, we found these 2 points. And we also know that we want the negative piece of the function equal to negative or 0. So the solution would be where? The solution would be in between, right? Would be in between. So these inputs would be the solution we're looking for. So we're looking for these inputs. Okay, so let's draw the line. Okay, so like this. There, okay. I'm going to draw the line to show you. Okay, and I can remove those. I can remove those hearts. So any input that's between this number, okay, -1 minus √2/2, or 2 -1 plus √2/2, any number between these two will give us negative function value or negative output or 0 output. So now what's the solution? We're not done yet. The solution okay, the solution is going to be the same. Okay, so I'm gonna emphasize that sameness by copy and paste. Solution right here. Solutions are right here. Okay, so by this time, I think you have seen, I would say, most of the cases, I would say 99% of the cases of solving quadratic inequalities. A lot of the ideas can also be applied to other situations. to other situations for other functions, Okay, for example, the idea of finding x-intercepts, right? How is this idea very, very useful? For quadratic function, we have quadratic formula to find x-intercepts. We can use the factoring tools to find x-intercepts, right? But quadratic formula solve all the problems, right? Not only that, it tells you when the x-intercept does not exist. And these ideas are huge. Similar ideas would apply to, say, sine function, cosine function, and so on and so forth, right? As we can see that we have seen some examples in the previous lessons in the past weeks. So if you look through the method we have, talked about, right? The ideas we've talked about, they all have something to do with the mathematical principles, right? Have something to do with the rule, right? So after all, we are dealing with what kind of questions? We're dealing with input, right? And we're dealing with a rule, and we're dealing with output. Okay, when we have input, vertical line, plug in, so on and so forth. When we have output, right? Output could be equal to something, output could be greater than 0, less than 0. It could be many different things, which we have seen plenty of examples here. Okay, so without further ado, I think this lesson is long enough. Thank you for watching. Until next time.